Well, that was not an easy quiz. To show you the answer, what we're going to do is we're going to calculate all these three equations, x plus y, x times y, and x squared plus y squared, at each one of the 8 points. So here we have our 8 points, minus 3 minus 3, 3 minus 3, etc., all the way to 1, 1. And the first 4 are red and the last 4 are blue. So let's calculate x plus y. At the first point, minus 3 is the sum of the two coordinates, which is minus 6. For the second one is 3 minus 3, which is 0, and all the way to 1 plus 1, which is 2. And let's see what happens to these values in the number line. So the blue points are mapped at 0, 2, and minus 2, and the red points are mapped at 0, 6, and minus 6. So there's still no clear cut, no place where we can cut this number line that will separate the red points from the blue points. And this is something we could have guessed before, because x plus y is a linear equation, and we've established in the previous video that linear equations do not separate these points, and therefore a line won't be able to cut this data. So let's try with the next one, x times y, which is not linear, so there is a hope. So x times y has the following values. Minus 3 times minus 3 is 9, 3 times minus 3 is minus 9, etc., all the way to 1 times 1 equals 1. And we plot these points on the line, and the blue points go at 1 and minus 1, and the red points go at 9 and minus 9. So there is still no separation. There is no way to cut this number line in two in such a way that the red points are on one side and the blue points are on the other side. So xy won't work either. Now let's try with x squared plus y squared. At minus 3, we get minus 3 squared plus minus 3 squared, which is 18. And all the other values are 18, 18, 18, and then 2 for the blue ones, since 1 squared plus 1 squared is equal to 2. So in our number line, all the blue points cluster at 2, and the red points cluster at 18. And now we can cut the number line in two, because if we draw a vertical line at 10, it can really be anywhere, but the best cut is at the middle, which is 10. Then we've managed to separate the points. So x squared plus y squared is the function that wins. And so basically what we have is that for the blue points, x squared plus y squared equals 2, and for the red points, x squared plus y squared equals 18. And how do you split a 2 and an 18? Well, let's say with a 10 that goes right in the middle. So our magic equation is x squared plus y squared equals 10, and let's remember that equation. Now we go to the circle, and what do you think the equation of this circle is? Well, x squared plus y squared is equal to 10. That is the circle that separates the red points from the blue points. But now let's go back to the building method, since I promised that the circle method and the building method were the same. So here I'll show you why. Let's recall that on the left we have a flat world, and on the right we have a three-dimensional world, which is a building with many floors. And our new axis is z. And our floors are at z equals 18, the 18th floor, and at z equals 2, the second floor. And the blue points are in the second floor, and the red points are in the 18th floor. So how to separate them? Well, by putting a separator plane in the middle, say in the 10th floor. And that's what the SVM does in 3 dimensions. It draws the best separating plane with the algorithm that we've learned previously. But now, how do we get a circle out of this? Well, if we consider the function z equals x squared plus y squared, that's this paraboloid. And this paraboloid intersects each one of the planes at a circle. The circle in the bottom contains the 4 blue points, and the one in the top contains the 4 red points. And the circle in the middle plane actually goes here, and it has equation, you guessed it, x squared plus y squared equals 10, since both of these values are z. So that's why the circle and the building method are the same, and they're both the kernel method for SVMs. So here's a summary of what's happening. Let's say we are in a 2-dimensional world, and let's say we have a set of points that cannot be separated linearly. So we embed our data set into a 5-dimensional world by taking the point xy and sending it to the point x, y, x squared, xy, y squared. As a small example, the point 2, 3 will be sent to the point 2, 3, 4, 6, 9. Now the data lives in higher dimensions, and maybe we're lucky that in here we can actually separate it with a 4-dimensional hyperplane. Well, now we go back and project that to the 2-dimensional world, and we get a polynomial of degree 2, which will nicely separate our data. This is called a polynomial kernel, and a kernel really means a set of functions that will come to help us out. So to show this is a similar data set twice. And if we use a linear kernel, that's like a bag with tools, and our tools are the variable x and the variable y. And we're looking at all the functions that we can build as linear combinations of these two variables. So we can create, for example, 2x minus y equals 1, or 5x minus 2y equals 3, or x plus y equals 4, basically any line. But if we extend it to a polynomial kernel, now we have the following tools. We still have x and y, but now we also have x squared, xy, and y squared. This gives us a lot more room to build functions to separate the data. So now we can construct circles such as x squared plus y squared equals 1, or hyperbolas such as x times y equals 1. And here I only drew half of the hyperbola, but that's okay. We can construct parabolas like this one at y equals x squared, and in general we can create a lot more functions and build a lot more boundaries. And the algorithm is exactly as before. We just add some dimensions to the data, find a higher dimensional surface, project it down, and we get our curves. And if we have even higher degree polynomials like this, well, we can create them with the polynomial kernel of a higher degree, say 3, which has all these degree 3 monomials as well. And in general, the degree of a polynomial kernel is a hyperparameter that we can train to find the best possible model.